I got a question last week about complex joints and why using generalized coordinates is helpful. So let's think about that for a few minutes. I introduced this idea of generalized coordinates last week to help us deal with situations where we have something that doesn't really behave like a nice, easy hinge joint or ball and socket joint. The shoulder is a really good example. I think the knee joint is another pretty good example. But here's the problem with using our traditional way of thinking about joints for a complex joint. So traditionally, we've got we could say, okay, well, this is a ball and socket joint. And that's fine. It has 3 degrees of freedom because it can flex and extend. It can internally and externally rotate, and it can adduct and abduct, which is shown over here in this diagram of shoulder motion. Oops, I guess that's elbow motion. But here's the problem with the shoulder. Not only can you rotate about the glenohumeral joint here, but the shoulder blade, the scapula itself, actually moves around. So and not only does it move around, but it's not sliding on a plane. It's sliding around on the rib cage, which is sort of this ellipsoidal, sort of elongated sphere. So we can't just say it's sliding vertically and horizontally, because then it would just kind of fly up and take off off the surface of the rib cage. So you also would need 3 degrees of freedom of translational motion. Maybe I'll just note that this is rotational degrees of freedom. Now, I didn't spend a whole lot of time last week on translational degrees of freedom because generally they're not relevant. The whole point of a joint is that it takes one thing and it sticks it to another thing so that you don't get translation, right? Your elbow joint doesn't come apart. But there are a few places where you do get translation in the body, and the shoulder blade is one of them. So the problem is, if we're going to try and think about the position of the shoulder, we have this big mess of full 6 degree of freedom coordinates. We would need the XYZ position in space of the shoulder blade and the 3-dimensional angle of the glenohumeral joint. The idea with a generalized coordinate, and there's mathematical benefits to this that you don't need to worry about, but from a conceptual standpoint, it's very useful to collapse all of this complexity of sliding around on the surface and blah, blah, blah into a much more compact representation. One way to think about it, the shoulder is imagine the whole rib cage is like the Earth. And on the Earth, we have latitude and we have longitude as coordinates. So you could think about the position of the scapula having it can go up and down on the surface of the rib cage, or it can go left and right on the surface of the rib cage. So we can collapse this to just 2 degrees of freedom that's sliding around on here. And we still need 3 degrees of freedom here, but this allows us to kind of separate these because, again, this is a technical point. You don't need to worry about this, but if you are not using this generalized formulation, these two interact with each other, and so you can't change one of them independent of the other. But again, more of a technical point on the math side. Where this strategy really helps, well, let me just back up and talk about a situation before I move on to the knee joint. Let me talk about a situation where this would be really helpful. I alluded to this last week, but if you are coaching athletes doing overhead motions, like a standing press or pull-ups or anything, quite often it's useful to be able to talk about what's the orientation of the shoulder. So how much flexed or extended is it? How much abducted, adducted is it? How much rotation do you have about the shoulder joint? And also simultaneously talk about where the scapula are in terms of their position medially and laterally. So that's on this generalized coordinate. And vertically, I think people usually refer to it as elevation and whatever the opposite of elevation is, depression. Yeah, elevation and depression of the scapula. But it's useful to think about how those two are not, that's not just moving around on the frontal plane, that's sliding around on the surface of the rib cage. Where this generalized coordinate idea can be really helpful also is at something like the knee, where you have really complex motion of the femur translating up as it rotates. So you'll notice, like say the rotation center, if relative to this point, where the tibia is going to sit on this, if the knee is straight, is going to be this far, and where it's going to sit right now is this far. It's much further. And so when you extend the knee, not only is the knee extending, but the femur is translating upwards, the patella is sliding up because it's being pulled by the tendon here, and you can't really see it in 2 dimensions, but the tibia is going to internally rotate. The idea with the generalized coordinate, take this, not only is this is actually more than 6 degrees of freedom, because you also need 3 more degrees of freedom for the patella. The idea is take this mess of like 9 coordinates, collapse it to 1 degree of freedom. So we can talk about the idea of knee angle. And yes, mathematically, we would have to kind of prescribe how all this happens, but conceptually, we can think about, okay, as you straighten the knee, here's what happens. The patella moves up, the knee extension angle increases, the tibia rotates internally, and I guess in this case, the femur would translate down because we're decreasing this distance. So you don't need to memorize exactly those things I told you about the knee joint, but what you do need to know is that this concept of a generalized coordinate is super useful for exactly these kinds of situations. And in this class, I'll be using this concept to talk about what happens at complex joints in a really simple way. So I hope that helps understand why we might want to use these generalized coordinates, and even just from a conceptual framework if we're not doing any math with them.